The Big Bang Theory is huge. It informs the origins of the entire universe. However, there's a lot more to this theory than just a colossal explosion. It also explains how the universe continues to expand, and it sheds light on the birth of new stars. Hi, I'm Rich Burnett for Wondrium. In this episode of Perspectives, 5 experts discuss the development of the Big Bang Theory and its many lasting effects. We begin now with an overview of the theory itself and some insights into why it was initially panned by the scientific community. Enjoy.
The current theory of the history of the universe is called the standard cosmological model. Based on evidence from a wide variety of telescopes and from theoretical models, astronomers have deduced that the universe began about 13.7 billion years ago in an event called the Big Bang. The Big Bang wasn't really an explosion as much as the sudden appearance of space-time with an equivalent temperature of about 1 trillion degrees. In a billionth of a billionth of a billionth of a second, space expanded by 1 billion times, an expansion that continues to this day, although at a much slower rate.
Scientists hated this idea. First of all, we don't see this sort of event regularly and have never seen versions of it under laboratory conditions. Why should we think such a thing happened? Unique events seem utterly unscientific. To claim that we can rewind the film to a point where all mass and energy is concentrated at a single point only to explode into a universe like ours is tantamount to theology. It's positing a creation event that grossly outruns what we can infer from the fact that the galaxies are moving away from each other. If you want to say there was a Big Bang that brought our universe into its current state at some point in the past, well, what caused it? And what happened before that? These are questions for which there could not even possibly be empirical answers. They aren't scientific questions. The Big Bang Theory itself thus seemed like fantasy, not real scientific work. There were scientific advantages for a Big Bang Theory. If it were true, then it would offer a solution to a problem called Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers. Problem's simple. Proposition 1, space is big, really big. Proposition 2, there are lots of stars out there, lots and lots of stars. So, putting 1 and 2 together, if you point to any spot in the sky and travel in that direction far enough, you'll eventually hit a star. Proposition 3, stars shine. That is, they emit light, right? That's what we see up in the sky. Now, putting 1, 2, and 3 together, if every point in the sky leads to a star, and the light of that star is visible in the night sky, then the entire night sky ought to be glowing. It should be as bright in the night as it is in the day. So why is night dark? Big Bang Theory gives us a nice, easy answer. The universe is of a finite age. It might be true that there's a star along any line you point out, but it takes an amount of time for the light to get to Earth. And if the star is far enough away, the light hasn't had time to get here.
The idea behind the Big Bang basically goes like this. As the universe expands and space gets bigger, the matter in it gets diluted. This means that in the future, the density of the universe will be lower than it is today, and that in the past, it was higher than it is now. This also means that the universe was hotter in the past. If we go back far enough in time, we would eventually find a period in which the entire universe was filled with an ultra-hot soup of matter and radiation, all at temperatures of thousands of degrees or higher, so hot that even atoms themselves couldn't stay intact. These are the kinds of conditions that today you would find inside of a star. This hot era in our universe's early history is what cosmologists now call the Big Bang. This Big Bang theory makes many testable predictions, including that of a background of microwave radiation that should have been generated as the universe expanded and cooled. And today this background fills all of space. This cosmic microwave background was first detected in 1964 and has been measured at greater and greater precision ever since. As this and other evidence accumulated in support of the Big Bang, more and more scientists became convinced of the validity of this theory. Today, there's essentially universal agreement among scientists that our universe evolved from a hot state over a period of about 13.8 billion years.
The idea of a cosmic microwave background can be traced back to Ralph Alpher and Robert Herman, two American cosmologists who first proposed the idea in 1948. Working forward from the Big Bang and using Edwin Hubble's famous equation and constant for describing the expansion of the universe, they estimated a black body temperature of 5 Kelvin for the background radiation of the modern universe. It would be over a decade before several scientists either rediscovered their work or made their own predictions on how this background radiation could be observed, with estimates moving ever closer to the radiation's true temperature of 2.7 Kelvin. One of these scientists was a physicist named Robert Dicke, who had studied the question of the temperature of space for years and invented the most widely used microwave detector design while working at MIT. By 1964, he was at Princeton and hard at work on a painstaking scientific mission to search for and hopefully detect the cosmic microwave background, and with it, the first robust observational proof of the Big Bang. Several colleagues at Princeton had joined him in the search. Jim Peebles had recently written about how to detect and identify this radiation and was preparing to publish his results, while David Todd Wilkinson and Peter Roll began building a top-notch microwave detector following Dicke's design. This was, after all, the best design for microwave antennae in the world, a design shared by the Bell Labs antenna just up the road. Arno Penzias was born in Munich, Germany in 1933, and his life may well have been saved by a radio signal. At age 6, he and his brother were among the 10,000 Jewish children evacuated to the United Kingdom, a rescue operation known as Kindertransport, after a broadcast was sent out via BBC radio asking for foster homes for children fleeing Nazi-occupied parts of Europe just before the start of World War II. His family was eventually reunited in New York City, where he earned an undergraduate degree in physics from the City College of New York and a doctorate from Columbia University. Robert Wilson, a few years younger than Penzias, was born and raised in Houston, Texas, spending time in the oil fields where his father worked as a chemical engineer. He described himself as a middling student in high school, but following his father's footsteps to Rice University, he earned a degree in physics before moving to Caltech for his PhD. Wilson joined Penzias at Bell Labs, and the two began working with the Holmdel Horn antenna, a 20-foot radio detector built atop Crawford Hill in New Jersey. It had originally been used to capture radio signals from an early NASA communication satellite. When that communication project ended, Penzias and Wilson took over use of the antenna. They hoped to repurpose it for radio astronomy and study how radio signals interacted with Earth's atmosphere. However, when Penzias and Wilson first started pointing the New Jersey antenna at empty patches of sky, a standard step to calibrate the detector, they kept picking up the same background noise, a kind of microwave static. What's more, unlike Carl Jansky's detection of radio waves from the center of our galaxy, this static hiss seemed to be coming from everywhere, popping up in their data no matter where they pointed the telescope. Penzias and Wilson soon realized that what they had found at Bell Labs could potentially be this theorized cosmic microwave background, and placed a call to Dicke at Princeton to learn more about the phenomenon and share what they'd found. It just so happened that Dicke was in a meeting with his colleagues when the call came through. After hearing what Penzias and Wilson had found, he hung up, turned to his fellow physicists, and said, "Well, boys, we've been scooped."
When the Big Bang spread matter across the universe, it did so ever so slightly unevenly. So the force due to gravity was ever so slightly uneven. And matter started to attract other matter, well, unevenly. Eventually, a big collection of hydrogen and helium collected into a large cloud, contracting further and further under the influence of gravity. As the cloud of gases contracted, two properties increased: pressure of the cloud and the temperature of the cloud. At some point, thanks to gravity, the temperature and the pressure of the cloud got so large atoms got pressed together that the electrons in the atoms were so ignored and the atomic nuclei began to come together under the influence of the strong nuclear force. What I'm describing is nuclear fusion, and a star is born. Now, nuclear fusion gives off a lot of energy, and the pressure generated by this energy halts the collapse of the cloud further for millions, billions of years. But let's focus on what happens in nuclear fusion. Atoms literally combine their nuclei to make larger nuclei, larger atoms. And the conditions aren't like right after the Big Bang, when fundamental particles are trying to come together in the vast expanse of space. Well, they can't. The space is too vast. In a star, however, the atoms are crowded together, brought together by the inexorable force of gravity. To give you an idea of the conditions, scientists estimate that the inside of a star has a temperature of several million degrees and a pressure of over 100 billion times the normal atmospheric pressure on Earth.
After the Big Bang, all of the matter of the visible universe was all tightly clustered with tons of gravity. However, as the universe expanded, matter was farther apart, which means that the gravitational force drops over time, much like it does as a ball thrown upward at great velocities. This has consequences on the prediction of how the universe will expand after the Big Bang. If the mass of the universe is too small, the universe will expand forever, always slowing, but never stopping. If the mass of the universe is too large, it will expand for a long time, but eventually the gravitational force will overcome the expansion of the Big Bang, and it will stop and then crash in on itself. This is called the Big Crunch. And if the mass of the universe is exactly perfectly right, the universe will expand forever, always slowing, and eventually stop the expansion at time equals infinity. Those are the options: Big Crunch, expand and stop, or expand and never stop. 1, 2, or 3.
Hey, thanks for watching. If you'd like to learn more about the topics in this episode, the full list of series that these clips came from is in the description below. You can watch them all on Wondrium. And don't forget to subscribe to this YouTube channel for new episodes of Perspectives, and you can watch previous ones here.